Now that we know the basics of matrix transformations, we like to contemplate some natural geometric operations in the plane. The first of those operations is rotation. So suppose that we would like to rotate a vector in the plane. So recall that we can always specify a vector v as a scalar multiple of a unit vector u. So one of the ways that we can think about a unit vector is we can think about it as pointing to a point on the unit circle. So of course we can think about the angle between the x-axis and the vector u. Let's call that angle theta. So we can express the coordinates for u in terms of the two basic trig functions. So the x-coordinate will be cosine of theta, and the y-coordinate will be sine of theta. So if we're interested in rotating the vector v by phi radians counterclockwise, it's enough to first rotate the vector u and then scale. So let's call this rotated vector u prime. So we can see here that this rotated vector u also points to the unit circle. Since we've rotated it by phi radians counterclockwise, the new angle between the x-axis and the vector u prime is simply theta plus phi. So we can write down the coordinates for our new vector u prime as cosine of theta plus phi for the x-coordinate and sine of theta plus phi for the y-coordinate. So if we think about u prime as the result of applying a matrix transformation to the vector u, then there should be some matrix A so that A times u is equal to u prime. Using the basic trig identities, we can rewrite the x-coordinate and the y-coordinate as cosine phi cosine theta minus sine phi sine theta, and sine phi cosine theta plus cosine phi sine theta. Next, we can break this into the sum of two vectors. We observe that the first vector has a cosine theta on the x-coordinate and a cosine theta on the y-coordinate. Then we observe that the second vector has a sine theta on the x-coordinate and a sine theta on the y-coordinate. So we can pull these two values out as scalars. Now, if we think about these two vectors as the columns of a matrix, we end up with a matrix vector product. We recognize the vector on the right is exactly the vector u that we started with. So we've identified a matrix whose columns are cosine phi sine phi minus sine phi cosine phi, which we'll call T for the time being, which takes a two-dimensional vector and maps it to a two-dimensional vector. What we observe here is that T takes a unit vector and it rotates that unit vector by phi radians in the counterclockwise direction. So this gives us a partial answer to our original question of how can we rotate a vector using a matrix transformation. Since every vector v can be written as a scalar multiple a times u for some real number a and some unit vector u, we can see that by linearity of t, when we apply the matrix transform t to v, we'll get t times au. We can pull the a through to get a times tu is equal to a times cosine of theta plus phi sine of theta plus phi, which is the vector a u prime that we wrote down originally. So that's the rotation of our original unit vector u by phi radians counterclockwise. Now, going back to our original picture here, we can see that TV represents a scalar multiple of our vector u prime, we can see that the angle between v and tv is also going to be phi. So in fact, tv really is the rotation of our vector v by phi radians in the counterclockwise direction as we wanted. So let's take a second to do a concrete example to see how this really works in practice. So for our first example, we are going to find a matrix that rotates vectors clockwise by pi over 6 radians. So we now know that the matrix with columns cosine phi, sine phi, and minus sine phi, cosine phi will rotate all vectors when we multiply them on the left by that matrix counterclockwise by phi radians. Since we want to rotate clockwise, we indicate this with a negative angle. So for this example, phi will be negative pi over 6. Plugging in negative pi over 6 gives us the matrix. And since cosine is an even function and sine is an odd function, we can reduce this to the following. And so we get the columns root 3 over 2, negative 1/2, and 1/2 root 3 over 2. We can also use this to represent some familiar operations from graph transformations. So for the next couple of examples, we're going to fix a vector v whose coordinates are v1 and v2. So our first example will be reflection across the x-axis. So we can write down exactly what our transformation is supposed to do. It should take a vector and negate its y-coordinate. So to find the matrix representing t, we just need to see what t does to the unit vector e1 pointing along the x-axis and the unit vector e2 pointing along the y-axis. And there you have it, 1, 0, 0, minus 1. So for our next example, let's do reflection across the y-axis. Similar to reflection across the x-axis, this one simply negates the x-coordinate. So again, to get the matrix that represents our transformation t, we simply apply t to the unit vector along the positive x-axis and the unit vector along the positive y-axis. And our final example will be reflecting across the line y equals x. So this is an important reflection. If you remember back to a calculus class, the way that you obtain the graph of an inverse from the original function is you take the reflection of the original graph across the line y equals x. So for example, if you want the graph of the logarithm, you take the exponential reflected across the line y equals x. This operation simply interchanges the x and the y coordinates. So to get the matrix that represents this operation, again, we just apply t to the unit vector along the x-axis and the unit vector along the y-axis. And there you have it. T of e1, t of e2 is the matrix 0, 1, 1, 0. Once we've developed some more machinery, we can actually tackle general reflections, but this will take a little time.